All right, in this video, I'll be going through paper 2 question related to the physics of waves. It says two progressive sound waves, y and z, meet at a fixed point P. The variation with time t of the displacement x of each wave at point P is shown in the figure 4.1. Use figure 4.1 to state one quantity of waves y and z that is the same and then that is different. Okay, we got to use the figure to do that. I think the period is the same, right? Because if you look at this wave, what is this one? Y, it has a period of 3 milliseconds, right? It's like the wave repeats right there. And if we look at, kind of go over here to 1 millisecond, that's where this wave starts. It goes over to 4 seconds before it repeats, and that's also 3 milliseconds. So what's the same about it? Period. Okay, and because the period is directly related to the frequency, or inversely related, I should say, so it's like the period 1 over the period is the frequency, then the frequencies are going to be the same too. So like you could say the frequency, but it's like, is that really using the figure or your knowledge of physics above and beyond the figure, right? So you say, well, if I'm really answering the question, I should say the period, right? In other words, they're giving me time data here, and I can read off the graph that the period is the same. I can calculate that the frequency is the same. I can understand that the frequency is the same based on a knowledge of physics. So I would say this is the best answer. They would probably credit frequency or, you know, I guess maybe even velocity because, well, no, I think use the figure. Period is the best answer. What's the obvious thing that's different about them? Amplitude would be the first thing I would go to also. Amplitude of the waves is obviously different. Wave y goes up here to 4 micrometers, and wave z over here is only getting up to 2. 2 and 4, nice round numbers, right? I can anticipate a calculation of intensity. State and explain whether waves y and z are coherent. Yes. Now we got to explain. Well, what does it mean to be coherent? It means two waves have a constant phase difference, and so we can just state that. They have a constant phase difference because their frequency is the same, because their period is the same. They don't change, right? It's not like this wave starts out at 3 milliseconds and then over here it modulates its frequency, right? Yes, the waves have constant phase difference. Now that doesn't mean that they're in phase, right? In other words, this wave is out of phase by this much, right? By 1 millisecond over the 3 millisecond period. It's out of phase by a third of the entire cycle. Okay, a third of 360 degrees, a third of 2 pi radians. Right? But the difference is constant. Okay, that's the key. It doesn't mean that they're in phase, it means they're out of phase. It means there's a constant phase difference. That's what it means for waves to be coherent. Waves are coherent. Determine the phase difference between the waves. So again, the way that you calculate this is what is the shift between them? I think the easiest way to read that is to look at this. This wave starts at 0, and this wave kind of starts above equilibrium at 1 millisecond. So they're different. The shift is 1 millisecond over the entire period of the wave, which we already saw up here was 3 milliseconds. So that's the difference. That's the shift, okay, compared to the total time period. So 1/3 of 360 degrees is what? 120 degrees of phase difference. And you can always look and see, are you restricted to certain units? And here we are to degrees. And so if you love, radians, converted into degrees. I think they would probably credit it. You avoid crossing out the units that they sort of tell you to, report it in. So I love light years, distance, forget meters, and you convert everything into light years. Don't make it harder on the examiner. Like we got an answer last class of like 16 meters per second, the velocity of the wave. You don't say, well, I like the square root of 256 for that. Just write it. I mean, because then you could have negative, right? Probably more negative. So, not only is it incorrect, but, it's more work for the examiner. Just report that number, not this one. Or squared. Oh. The two waves superpose at P. Use figure 4.1 to determine the resultant displacement at time 0.75 milliseconds. All right, so at 0.75 milliseconds, we got to sort of find that on here, and then they're superposing. Remember, this whole thing is two progressive sound waves meet at a fixed point P, the variation of the displacement of each wave at point P. So you're looking at that data right here, okay? At that point, as a function of time, how are the waves sort of, moving the air particles around? How much are they displacing them? And so our job here is to apply the principle of superposition, which you should have that in your notes. And the principle of superposition states something like, when two waves meet at a point, the resultant displacement is the algebraic sum of the displacements of the individual waves. Some statement like that in your notes. And so that's what we're doing here. We're taking the algebraic sum of the displacements of the two waves at this time here, 0.75. Note how equilibrium is at 0, and the particles can move above or below, positive or negative, okay? And so we'll find here, like, this is 1 millisecond, and so there's, I think, 10 lines, 1, 2, 3, 4, 5, that seems halfway, right? 6, 7. All right, so there's 10 lines, and so we had to get in between the 7th and 8th line. 1, 2, 3, 4. Yeah. 1, 2, 3, 4, 5, 6, 7.5. So right here, oh, wouldn't you know, that's one's at its maximum displacement there. I might even call them amplitude. And this guy down here, right there. It seems like in between these points. So there would be, this is -2, and this would be, let's see, 4, 8, 12, 16. So each of these is 0.4 micrometers, right? Every little square. So it goes 0.4, 0.8, 1.2, 1.6, 2. So if each little square is 0.4 micrometers, then this one goes down 1, 2.5 little squares. And so it goes 0.4, 0.8, 1, right? Right there. 1 micrometer. So the calculation is this. Algebraic sum of 4 micrometers plus -1 micrometer, right? Because this is below equilibrium, so it's -1 at this point. So wave Z has an air particle that's displaced this much. Wave Y has an air particle that's displaced this much. And because they're superposing, because they're coherent waves that are meeting in space, they're interfering, we're applying the principle of superposition. So the actual intensity of the sound wave is related to the amplitude here, 3 micrometers. The actual amplitude, so in other words, the combined wave at this point is right in between 2 and 3, so it'd be right here. So this would actually be the sum. And if you were to sort of add up everywhere, like let's do that to every single point, right? We'll just stay here until we're in the 4th block. We would get sort of like what the new wave would look like. And we could look at a few points and say like, is there anywhere where the wave just cancels out, or it's at 0, or like this is just as high above as below? But you get the idea, right? Like you do the same calculation everywhere and you get the new combined wave, and it'll be some combination of them. And that's the actual wave that would be observed, right? We can't sort of separate out the individual waves. Now there are sort of mathematical formulae that can do that. Any like cue and speech, or any a symphony of instruments, right? It harmonizes because all those instruments are sort of playing together there. But there's ways to sort of separate out not just the individual sort of instruments. You can separate out the individual sine waves that make a more complicated sort of waveform. With I've mentioned before, Fourier transform. Very useful. So 3 micrometers, we don't need to convert that into meters. You know, again, you don't get in the habit of like scratching that out and putting in light years or something like that. How many light years is 3 micrometers? All right, so finish this one off here with, it says the intensity of wave y at point P is I. Determine in terms of I the intensity of wave Z. In terms of I. So start with, okay, so I intensity, all right, and what can we read off the graph was the amplitude. So intensity proportional to amplitude squared. The intensity of wave y at point P is I. Determine in terms of I the intensity of wave Z. So the intensity of wave Z compared to the intensity of I, wave y, equals the amplitude squared of Z over the amplitude squared of wave y. And wave y was the taller one, right? The 4 micrometer amplitude. And wave Z was 2, right? 2 micrometers. 1. If we multiply both sides by I, then we'll have the intensity of Z in terms of I, right? So it's going to be 2 squared is 4 over 4 squared is 16. So we got 4 over 16I, which is 1/4 I, or I over 4. I kind of like 1/4 I. Because wave Z has half the amplitude of wave Y, its intensity is 1/2 squared as much. Okay, 1/4, because it goes as a square. They give us the speed is 330 and we want the wavelength of Z. So let's remind ourselves that velocity is distance, which is wavelength, divided by time. The same velocity we've always learned. Distance divided by time. But time for a wave is related to frequency like this. And so this is why we sort of think this equation is more useful when it comes to waves, because we can typically sort of, you know, we want the frequency, right? But it really is the same definition of velocity, distance per time. Time of a wave is a period, right? And 1 over this, so just substituting that in here gives you that. I think we want to use this one for this calculation. Do we know the wavelength? Oh, we're determining the wavelength. Okay. So we're just going to say lambda equals P, and they give us this is 330 meters per second, and we already saw that the time period was 3 milliseconds, I think. There's 3 milliseconds, right? So 3 milliseconds. All right, and that should be enough to solve. I mean, you could like calculate the frequency and then plug it into the other equation and manipulate that, but it's just like, you know, this is the most straightforward way based on what you're given. 330 times 0.003, 0.99. Almost 1 meter. Bless it. All right, 3 marks for that one, and that was a total of 10 marks on that one. This has been another Paper 2 Waves Physics question with Dr. Schleich. We'll see you next time.